Okay. So we looked at non-deterministic Büchi word automaton, where the notion of an accepting run is essentially it's like an the run is an infinite sequence of states, right? And then uh, the idea is that these states are essentially their existential states, in the sense that if you want to accept a word, you have like which is like AW, then you have a successor which is Q prime. There exists such an A successor from which you can uh, accept the remaining word, the suffix, right? And one can also think of universal automata in which you have like there are different, if there are different successors, then from all these successors you have to, like, there should be runs and you should be able to accept the suffixes. And alternating automaton is essentially like you can have the set of states which are being partitioned into like this universal and existential states one can think of. But we also say some existential states, you can think of these as if like the three A successors, Q1, Q2, Q3. Then you can think of like the run being accepted for the suffix from one of the successors, so like a disjunction. And if you have a universal states, you can think of like it's a conjunction, because you want to accept all all the runs from all the successors, right? And now we say that more generally, you can also think of like this is like the delta, the transitions are like formulas, and you can also think of that the transitions are formulas of arbitrary type. They can be mix of both disjunction and conjunction, right? So we discussed something called this positive Boolean formula, in which there is no negation on the state. So it's you have conjunction, disjunction, etc., but there is no negation as such. And so the set of positive Boolean formulas, they were denoted by this B plus of Q. And we also said like if there is a transition which gives you a formula which is true, that essentially means that everything after this is accepted. And if it is false, then essentially such a transition cannot exist, because false is not satisfied by any state, and so on. So now, um, okay, so let me go over this. There was also a question somebody asked, like, if we have such formulas, is it equivalent to like where you have only existential and universal states, right? I mean, if you just, so we said like you can also think of alternating automaton where the states are just universal states and existential states, and we said that, but we can think of even more general case where this can be arbitrary Boolean formula now, if they're equivalent, right? So there are, the first answer is like what we know is that alternating automata, they are Bushy automata. They are no more powerful than non-deterministic Bushy automata. So this is something we'll see today. So which of course means that like, okay, you can essentially, given such an alternating automaton where you have these formulas, you can essentially translate this to an automaton where you have only existential states, right? So of course, these having this formula is no more powerful than having states which are both universal and existential. Uh, um, well, I mean, one can also ask this kind of questions if there's an easy way to translate from automata where you have such formulas to automaton where you have like only the existential and universal state. So we'll try to look at that. Um, Now, okay, before I get into that, so these are the definitions we looked at. Like, so you have this B plus X is essentially a set of Boolean formulas. We saw over X for this set X, and then also the formulas can have true and false. And then we say that Y satisfies a formula theta if the variables in y are set to true, and the other ones which are not in y, they are set to false. And y also satisfies theta in a minimal manner if no strict subset of y satisfies theta. So as an example, if you have something like this, that q1 or q2 and q3, then all these three subsets indeed satisfy the formula, but q1, q3, and q2, q3, they satisfy it minimally. Okay. Now, the runs, how do we define the runs? So we say that the runs of an alternating automaton, like one run, it looks like a tree, right? So even for the universal automaton also, if you think so in a universal automaton, essentially, if you see that you just have one run, because you were saying that along all successors you have to you have to accept, right? So so even the run of a universal automaton also you can think of as if it's a tree. In fact, like if you have the disjunction and the conjunction, so the conjunction gives you a tree and the disjunction gives you choices of different trees and so on. So now we also defined formally what is a tree. It's a prefix closed set, and the root of the tree, it's called a node, and this is like the run is essentially a queue labeled tree. So each node, how is a node, how does a node look like? A node is essentially a subset of n star. Sorry, a set of nodes is a subset, like the tree is a subset of n star, and each node is a concatenation of these natural numbers, right? So where each of these natural numbers, this kind of gives a direction to the successor. And so we also have the label, we also define the path, and we say that this is a queue label tree. And how was it? Like it was that the labeling is, so R is the labeling function, so it has a node q, and then if the transition defines formula theta, then a particular run will have a set of states such that this set of states minimally satisfy the formula theta, right? So this is pretty much what we discussed. And then we also, yeah, we say that a word is accepted if there exists an accepting run. And what is the notion of an accepting run? So you have all the paths, and all the paths should be accepting, right? So all the paths should visit alpha infinitely often. Okay, good. And we also looked at such an example where you have like, so this language was essentially like you have the alphabet which had 1 to n, and we said that this alternating Bushy word automaton n, it accepts all words with the subword I for all letters I in sigma n, right? So for example, like if you have n equal to 4, then this is like it should have all these factors or all these subwords, right? 333, 111, 222, 444, all of them, they should be there. So how does the automaton it looks like? So the state space is essentially like we have an initial state which is q0, and then we have sigma n cross 3 to 1, right? So the idea of some state which is of the form I comma c, where c belongs to c is either 3 or 2 or 1. So I comma c, it means that it is yet to see another c i's, c contiguous i's. Okay, it's yet to see another c contiguous i's. So if from the state I comma c, if you see a letter J where J is not equal to I, then again you have to go back to I comma 3. That means you have to see 3 consecutive I's. Clear? So
Uh, I have a question. So, this 333111, so this has to occur infinitely often or just once?
no,
It
this
has
is
to occur in.
just once. Just once.
Okay. So, then how is the Buchi condition, matlab, then how is it different from any alternating automata? Just alternating automata and alternating Buchi automata.
No, it can be, I mean, you can even think of like if it is over finite words, I mean, you can also think of this like an alternating automaton over finite words, where the finite word will have these things like this contiguous things from 1 to n for each of them. The only thing is that, like you say there, that you will reach there an accepting state. In the case of finite words, here also it's pretty much the same. Like you will say that you reach there and you reach an accepting state, which will be, let's say, this is an accepting state or a good state in the case of Bushi thing. And then you say that, okay, once I have reached, then I can read anything and I'll be here only. Okay, I can read anything, the entire sigma and I'll be here only. And this
Ah,
example
I
is
see.
similar to the over the finite words. Like this is your final state, and once you reach there, you are fine. So in this example, indeed, there is not much of a conceptually, it's not much of a difference between over finite words and the Bushy words.
Hmm. Okay, okay. Hmm.
Yeah, go. So, and then from the initial state, how will the transition look like? That from the initial state Q0, if you read an I, then since you have already read an I, you will go to a state I comma 2, which essentially means that I need to read another two I's, uh, one after another, uh, right? And then you also say that for all the other j's, where j is not equal to I, you need to see three uh, contiguous contiguous j's, right? And then if you were at I comma 1, when you read the I again, then you reach, then the transition is that it should be true, right? So after that, you are good. And if you are in I comma C, then when you read I where C is 2 or 3 greater than 1, then you reach I comma C minus 1. So this is pretty much like what we said. And this is the thing here, right? So now coming back to that question that was asked, yeah, last time. So yeah, I see Rishabh is here. So I think the question was the following, that if you have something like these formulas, then is it, I mean, in some way, like, is it equivalent, or can you, yeah, I mean, the answer to the question that whether it is equivalent to an automaton with only such states which are existential and universal, that is kind of easy from what people already know, because there is this notion of alternation removal, which we will possibly see towards the end. Alternation removal, which means that there is a construction. What it does is that this construction will start from an ABW and it will translate to NBW. So that means that ABWs do not recognize anything more than omega regular languages. So they are as powerful as NBWs, right? NBWs are no less powerful. ABWs are no more powerful than NBWs. So this is one thing. But okay, now the other thing one can also, the way to look at this maybe is like, okay, we can look at, for example, the syntax tree of this formula, right? So if I have something like this kind of a formula q1, so this is my, let's say q0 is my initial state, so this is an abw, and I essentially want to look at this as an automaton with such states, right? So what I can do is that if I look at the syntax, at the top there is an and then I have like an or, and which is this q1 q2, and then there is a q3. Okay, so what I can say is that to start with, I have,
পড়ছি, ক্লাস চলছে।
so yeah, so what we can say is that initially I have Q0, and this is like a conjunction, and I can to one, go to some state, which is like, so this is like a Q, so this is like a Q3, Okay, so this is, since at the top there is a conjunction, I'm going to treat this as a universal state. Okay, I'm going to treat this as a universal state. Now here I will treat this as a as an existential state. Okay, so Q1 or Q2. So this is like my one state, which I am calling it. The state itself, I am calling it in with certain name, and this is a this is an existential state, right? And now I can see what is there from Q1. So uh, one second. So now I have from this Q1, let's say I'm reading here, here an A, right? And then from here, I'm going to read a B. So Q1B, I can go to Q4. And so what are the different possibilities like Q4 and Q5? Let's say I'm reading a B. This is the word. And Q2B is like Q2 itself, right? So the thing is, um, so this is one run, and the other thing is from Q to B, I'm going to a Q2. Okay, so let me, yeah, um, right. So now this thing again, here the Q4 and Q5, I can again consider this thing as a universal state, right? And I can continue like this. So do you see, like, so I'm looking at the formula, and uh, so Q1 or Q2. So this is so here I read the B, I go to Q2 again, and Q1 I'm going to Q4 and Q5. Now this is again, since there is a conjunction, I will treat this as a universal state. So let's say from Q4 I have something like this. So from Q4 I go to Q10 and Q11. Let's say I'm reading an A here, or Q12, and uh, and from Q5, I'm reading, let's say, Q14 or Q15 and Q16, like this, right? So I can treat each of them. I can look at the formula and then look at the tree, and I can just treat them as a universal and existential. And now you can see that essentially, like if you say, for example, there is an and here, then you have to take both the branches here, because I'm considering this as a universal state. So on, right? I mean, you can just proceed in this way, and you look at the top and the topmost symbol, and you can proceed, and this should be, this is equivalent to what we have, right? So Vishal, does it give your
Yeah.
is it clear?
Yeah. Makes sense. So every state now will either be a bunch of ors or a bunch of ands.
Right.
And
Right, but
yeah.
yeah, like so, but I mean, what we know here is that from here you can directly get, of course, that this is the NBW is already, for example, it's as powerful or as expressive as the ABW, and the NBW even doesn't have the universal state, right? So if you add the universal states, of course, that will be that can be syntactically it's more expressive, but so that of course gives you the answer that having the universal and the existential states, I mean, it's that should also be equivalent to the kind of things that we are looking at, right? And then you can easily translate such things to an automaton where you have only universal and existential states. Now, there will be one question you may have, like this is something I was just trying, like given that he asked this question, that when you are doing this construction, so what is the natural thing that may come to your mind? Like, what is the next question you would like to ask? Like, I mean, what is
So yeah, I mean, maybe from a state on multiple letters, we will have multiple such formulas. So there'll be so many
Yeah,
state.
right. So the question is that what should be the, like, the, if you look at now the state space, is it going to be like how big the state space is going to be? So I mean, I have not really worked it out, but I mean, this is something you should think yourself, but I believe this will be exponential at least. Yeah, right. So this is something you can try, but I believe this will be, there will be an exponential blow up when you are sort of doing this translation, because you can have these different combinations and subsets, and along with that also the Boolean connectives, right? So with all that, yeah, right. Okay, good. But this is something you can do yourself, right? So what should be done? Yeah. Okay.
So, one more question. So, this ABW is equivalent to NBW. Is this also true for the finite case, मतलब alternating
Indeed, yeah.
automata
It's
and
also the case
I see,
for finite, yeah, for automata over
I see,
finite words, you can remove the alternation. There also you get
I see.
an exponential blow up. Indeed. So it's that alternating
Okay,
automata are exponentially more succinct. Okay. So
I
there
see.
are
Okay,
results again like lower bound results, which we will not see. I'll just possibly refer to the work for Bushy automaton, but we'll look at the translation, the algorithm for translating and alternating automation today. Okay, good. So we looked also at the closure properties, right? So you start with an initial state Q0, and then you just say that so you add such transitions like delta of Q0A is delta 1 of Q01. So these are your input automaton. So your delta 1 is there is an input automaton A1, there is an input automaton A2, and you have their transition functions are delta 1 and delta 2. So if you talk about union, then you just have delta 1 of Q01 comma A, or delta 2 of Q02 comma A, right? And delta Q0 A. So this is a new state that we added. And the remaining transitions remain the same. And you can also have, similarly, you can also define intersection, where the only difference is that instead of a disjunction, now you will have a conjunction. Okay, so it's that simple. For if you look at alternating automaton, union and intersection is very simple, right? You just have disjunction, conjunction, all of them are at your disposal, you just have to use them, right? So this is what we did in the last lecture. Today we are going to look at the complementation. So you have any questions? Fine, okay, good. So for the complementation, we'll first look at something called dualization. So the idea is the following, that you have the formula, we will construct dual formulas. And then this is something you can try to convince yourself that when you have, for example, let's say, Bushy automaton, alternating Bushy automaton. Now the automaton after this dualization, I will go over that what the dualization means. After the dualization, we should look at that automaton as a Kobushi automaton, right? We are looking at the complementation. So the paths earlier which were being called, they were accepting. So now they should be like rejecting. Okay, because suppose you visit alpha infinitely many times, you want to now say that I visit along that automaton. So there is no change in state space or anything. It's just like, yeah, after the dualization, you will say that those paths should visit alpha only finitely many times, right? So that's like a Kobushi condition. So so the idea is that, so there are two things here. If you have the A, which is the ABW, right, alternating Bushy word automaton, we start with, let's say, the complement. We construct the complement automaton, where you have now a delta tilde, which is obtained by the dualization, and also we have the acceptance condition, which is also a dual acceptance condition. So if you have Bushy here, then you will have Kobushi. Clear? So how do you dualize? Like if you have delta QA equal to theta, then delta tilde QA is theta tilde, where this is obtained, the theta tilde is obtained by switching true to false and the or to and vice versa, the and to or and false to true and so on, right? So this is the true to false and to odd and vice versa, like false becomes true and odd becomes and so on, right? Now you can just sort of try to like convince yourself that this essentially gives you the uh, complement automaton when you also think of this as the dual condition, right? So if this was Büchi, then this has to be a co-Büchi acceptance, right? So um, okay, so this is a result, I mean, which is possibly you can try to see. It's like, so for example, in the Büchi automaton, if you have a negation, sorry, if you have a conjunction, right? So now in the dual transition, it will become a disjunction, right? If suppose both of them were accepting, right? So suppose it's a conjunction, both the along both the successors, it's if it was accepting, you want to in the complement automaton, you don't want to accept, right? You want to reject. So essentially, both of now the conjunction becomes a disjunction, and both of them are now rejecting, right? So it is not indeed accepted, right? So on the other hand, suppose it was a disjunction. So along one path, it was accepting. The other path, let's say it was rejecting. Okay. Now when you have the conjunction, then what happens? Like again, one becomes in the dualized transition, it becomes a conjunction. One remains accepting, one remains rejecting, right? And essentially, that will also not be accepted by the Kobushi condition, correct? And the definition of the path accept reject also it changes, correct? Right? So you can convince yourself, and it's not too difficult to see. And what it says, this particular result, it says that if A is an ABW, right, accepting L, then A tilde, the way we defined this A tilde, so by dualizing the transition function and by dualizing the acceptance condition, is that this accepts the complement language. Okay, so now we are going to look at actually the complementation construction. So this part we already understand, right? That given an ABW, we can construct an ACW, which has the complement language, which accepts the complement language. Now we are going to look at this part, okay? Because we started with an ABW, we are trying to get an ABW which accepts the complement language, right? So we are going to look at this part, so which is ACW to ABW without changing the language, because we have already complemented in this part, right? We don't want to change the language anymore. So, so this construction is there in this paper, okay? Uferman Vardy, TOCL, the reference is there in that chapter, but the construction is not entirely there in the chapter. It just refers to that. And so this is a paper from TOCL. This is a journal paper which is called Transaction of Computational Logic. Okay. So yeah, Uferman Vardy from 2001. So yeah, so we are going to look at this construction, like given an ABW with n states, there is an ABW A prime, right, which accepts the complement language, right, such that A prime has order n square states. Okay, it has order n square states, and we will see that indeed, like the translation here, it uses concepts. You remember that we had this like a run tag we used for the complementation of NBW. So it will be using those similar things like the run tags and whatever we saw there, those concepts will be uh, useful. Okay. Now, one of the things is that this complement automaton that we are going to construct here, this A prime, this is something called a weak alternating automaton. Okay. And in fact, we'll see when people talk about weak alternating automaton, it can be a Büchi automaton as well as a co-Büchi automaton. I mean, we don't refer to that often as a weak alternating Büchi or weak alternating co-Büchi. Why, it will be clear soon. Okay, so weak alternating automaton can be thought of as both a Büchi as well as a co-Büchi automaton, right? So people just call it a weak alternating automaton rather than calling it a weak alternating Büchi automaton or a weak alternating co-Büchi automaton, right? So let's see what is the notion of a weak alternating automaton. So this was from by Muller in 1986. So the Muller automaton we saw, right? So this is so the idea of the weak alternating automaton is that so you have the acceptance condition. Okay, so for now think of this as a Büchi automaton. Okay, but we'll see that you don't need to really call it a Büchi or a Ko-Büchi. So the idea is that you have the acceptance condition alpha similar to Büchi acceptance condition, and you partition your state space. You partition your state space into these disjoint subsets Qi such that either Qi is a subset of alpha or Qi is disjoint from alpha, right? So you have partition into different parts. So I'm calling each part Qi, and either it is entirely contained in alpha, so all the states are either good or none of the states are, right? So this is one thing. In addition, there is a partial order which is less than equal. So what is the partial order?
All need not be related, but
Huh.
they're either greater than.
Yeah, so some of them
Some
are
of them are.
related. And if it happens that A less than equal to B and B less than equal to A, then
Then they're
A equal to B, right? So, so do you know how is partial order different from a pre-order, let's say? Like what is a pre-order or a quasi-order? So what is an equivalence relation? What is an equivalence relation? So anybody among the online participants also can say?
Uh,
We can separate the set or whatever we have into a bunch of equivalence classes.
Yeah.
Such that everything in a equivalence class is equal and no two things in different.
I mean, equal, it may not be really, yeah, I mean, may not be really equal, but they are
Like related.
equivalent
But
with something. Yes.
equivalent.
Yeah,
But no two things in two different equivalent classes are equal.
equivalent. Okay. Yeah, somebody was saying in the audience.
no, yeah, I mean, I was just saying, about to say the same thing. That's
Okay, so there is a more formal way of saying, like, I mean, this is so an equivalence relation. You know what is a reflexive relation and so on, like a relation is reflexive. So how do you define an equivalence relation that way?
like symmetric and.
Reflexive symmetric. Good. Reflexive symmetric transitive. Okay. Now, so these things I'm just saying because yeah, these are important and one should always know what they are because you would often come across these things sometime or the other. What is a pre-order or quasi-order? So something is a pre-order or a quasi-order if it is reflexive and transitive. Okay. Reflexive and transitive. Okay, so this I mean, we call it a quasi-order. And what is a partial order? So you know what is, I mean, you understand what is meant by reflexive, what is meant by symmetric, what is transitive.
What is reflexive?
So reflexive means that R is related to R. So suppose I'm talking about a relation R, right? So let's say I'm talking about a relation R, okay? So reflexive, suppose you say that X, comma X will belong to R for all X from your set, okay? So then you call that R is reflexive, okay? And you say something is symmetric, you understand?
Yeah, if XY belongs to R, then YX belongs to.
Yeah, and what is transitive? Either XY belongs to R,
YZ belongs to R, then XZ belongs to.
right? So this is reflexive. And then, so this is equivalence relation, and then we say what is a pre-order or a quasi-order, and what is an partial order. So this is like reflexive. So it is of course a pre-order first. Reflexive, transitive. So it's a partial order is a quasi-order or a pre-order, and then on top of that it is antisymmetric. So what is antisymmetric?
Like if XY belongs to R, then YX does not belong to.
No. that is called asymmetric. If xy belongs to, like what you say, if xy belongs to R and yx belongs to R, then x equal to y. Okay, xy belongs to R and yx belongs to R implies. Okay, so this is antisymmetric and this is called a partial order, right? So every partial order is also a pre-order or a quasi-order, right? So these things you should never forget, like what is a pre-order, what is a quasi-order, what is an equivalence relation. I mean, when people ask you how to define an equivalence relation, you should not say that, oh, these are equivalent. You should say it's like a reflexive, symmetric, and transitive. And a partial order is one which is reflexive, transitive, and antisymmetric. Okay, good. Right. So now what we are saying is that now there is also a partial order on this QIs, on this state, on these parts. Like we had first, we said that okay, you have this partition of Q, and then there is also this there is also a partition. There is a partial order on this sets QIs, right? So how is that partition? Like in that automaton, so if you have a transition from some Q belonging to capital QI, some state, and there is a Q prime belonging to capital QJ, okay, for some A, for some letter. So if you're making a transition, then Qj is less than equal to Qy. So what does it essentially means? That so transition from a state Qy, from some state, it always, like if you're going from one state to another, you are always going to a state which is not bigger than the source state, right? You are always going to something which is equal or less, right? So that's the idea. Okay, so if you have these two conditions, then you call it a weak alternating automaton. So again, what is a weak alternating automaton? So one thing is that all the so first of all, you are partitioning the state space, and each part either fully belongs to the set of good states alpha, or it is disjoint from alpha. So this is one condition, and the second condition is that the transitions are going from one state to an equal or a smaller state. Okay, so that's the idea. Now you recall that we had something similar when we did the DAG, that construction, right? So we had an order, like we were defining this ranking function, and then when we were going from one to another, then we said that okay, like it has to be, the rank has to be less in that tree, right? Less than equal to. So I mean, similar things, ideas will be used. Okay. So now if you look at it, then you can also see that every infinite path here, just like those ranking function, like if you remember that there was a rejecting DAC, then it gets, all the runs get trapped in an odd ranking. Yeah, I mean, in an odd rank, right? And here also every infinite path, it gets trapped within some QI, right? Because it cannot arbitrarily keep reducing, correct? Because you can have, like, let's say you have some set of states in the automaton, right? Like it's an SCC, right? It cannot arbitrarily keep reducing, right? At some point of time, you will just get stuck in some, get trapped in some QI. Okay, so and we say that the path satisfies the acceptance condition if and only if QI is an accepting set. Okay, right? So that's the thing, because you cannot arbitrarily decrease, right? We are decreasing, like from one state to another state. We are either decreasing or we are like stay at the same level, right? So that's why if you have an infinite run here, for example, in the SCC, at some point of time you will get stuck in some QI, right? Some subset will get some part will get trapped in. Clear? Is it okay for the online participants? Right? Is this part okay? Clear?
Hi, so can you repeat the weak alternating automata part? My network got disturbed at that point.
Yeah, so you understood, did you follow this to the definition here? Like when I say that you have an accepting and like this, these are either fully contained or it's disjoint.
Uh, uh,
Okay, so let me repeat. So what I'm saying is that like this, so essentially the definition of a weak alternating automaton is that you there exists a partition of the state space Q, right? The alternating automaton. So the automaton has a state space, right? So what is the state space? The state space is capital Q, and I'm saying that you have a partition. So the state space is divided into several parts, and let's say which I am calling Q1, Q2, blah, 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 Qk, like this, right? So now I'm saying that each such Qi either belongs to alpha entirely, right? It's a subset of alpha, or Qi intersection alpha is empty. That means either all the states here is good state or none of the states is a good state. Clear?
yes, yes,
Right? So this is one condition. The second condition says there is a partial order on these sets. There is a partial order on these sets. How is that partial order defined? Like if you are going from, like if it is the case that Qi is less than equal to Qj, right? So this less than equal to is the partial order. If Qi is less than equal to Qj, then you have essentially like for every transition from here to for every transition from a state here to a state here, right? Uh, it like okay, sorry. Uh, okay, I think I wrote it in a slide in the different order, but anyway, doesn't matter. Yeah, I wrote it in Qj less than equal to Qi. Doesn't really matter, but Qj, Qi. So if this is the case, so it means that for every delta Qa, if you have, let's say, something like you have right, okay. So I'm saying that if Q prime belongs to delta Q of A, okay, Q prime belongs to delta Q of A, then it happens that Q prime belongs to Qj, okay, where and suppose Q belongs to Qi, and it should be the case that Qj is less than equal to Qi. Was it clear? So if you're having a transition from some state Q to Q prime, okay, so recall that it's actually a formula, right? Delta QA it's an alternating automaton. It's a formula, and in that formula, suppose Q prime appears, then Q prime belongs to something which is not bigger Q,
mm,
not a bigger set.
mm.
What, okay?
Okay, got it, yeah,
So Q prime is either at the same level like Qi, or Q prime belongs to a set which is smaller. Okay, so that's the thing. So this is the definition of the weak automaton. Okay, now if you see, then you can see that any infinite path, like when you have a run, then every infinite path, it gets trapped. Finally, it will, suppose there is an infinite path which comes like this. Finally, it will get trapped in an SCC, right? There will be a strongly connected component where every infinite path it gets trapped. Like this, what we have seen, for example, in a Büchi automaton, right? You have an infinite run. So at the infinite run, at some point of time, it will visit a set of states infinitely often, right? And now all we are saying is that all these states which are visited infinitely often, they belong to one particular Qi. They belong to one particular Qi. All these states, right? Is it okay?
yes, yes, it's okay.
Right? Because you cannot infinitely, you cannot keep decreasing, right? At some point of time, you get stuck. So this is what right? And the acceptance condition should be like if this path particularly is it's an accepting path, right? You are visiting alpha infinitely often, then it should be the case that this Qi corresponding to this SCC should be a subset of alpha. Okay, so that's it. Okay, so right? And then from our discussion, what we just discussed right now, we can say that every SCC in WAA is either contained in alpha or is disjoint from alpha, right? So this is, I think, should be right. Every SCC would be either contained in alpha or disjoint in alpha. Now, I also state that WAA is a special case of a Büchi as well as a co-Büchi automaton. A weak automaton, weak alternating automaton. It's a special case of a Büchi and a co-Büchi automaton. Why is it a special case of a Büchi automaton?
Because we want all the states in the strongly connected thing to be accepted.
Right,
But Bushi just wants something to be accepted.
right.
So it's just special.
Right. So indeed, so the thing is, like, I mean, I can say that suppose the WAA with acceptance, suppose alpha, just the way we defined, it's like a Bushy, you can also call it a Bushy automaton with acceptance condition alpha, right? But now I am also saying that the same automaton with the same language, it can also be thought of as a Kobushi automaton with acceptance condition what?
Alpha complement.
Exactly. With acceptance Q minus alpha. Right? Because if you see the runs, suppose it's accepted by you consider the Bushy condition. So what does it mean? That if there is an accepting run, then the accepting run comes, and like if I mean of course it's a tree, but I'm just talking about, let's say there is an accepting path there, then there is this accepting path, it will be entirely contained in alpha, right? So there is a QI here. As we said, the QI is entirely contained in alpha, entirely, right? So which means that the states which are outside the alpha, Q minus alpha, they are visited only finitely often. Right? So this can also be stated as a Kobushi acceptance condition with Q minus alpha as the acceptance. So this should be visited only finitely often. That's the thing. Clear? So weak alternating automaton. It can be seen as a Bushy automaton as well as a co-Bushy automaton for the same language, right? So that's why people often don't refer to it as a Bushy or a co-Bushy. They just say weak alternating automaton. Clear? Okay, good. So now we will look at the translation with this. We said that, okay, so when you are constructing the Bushy automaton, the alternating Bushy automaton, I said that this alternating Bushy automaton A prime, it's essentially going to be a weak alternating automaton, and it will have n square states, right? If you start with a Kobushi automaton with n states, we will end up with a Bushy automaton having, or weak automaton having n square states. Clear? So let's see how the idea is essentially it follows those the idea of those ranking functions and then the rejecting DAGs which we saw. But well, I mean here it's uh, not exactly a rejecting because we start with a Kobushi automaton. So you see those alpha only finitely often. So it's an accepting run of the Kobushi automaton, right? Earlier we were talking about a rejecting run DAG, right, for the Bushy automaton. So where you keep track of all possible runs in the ABW. Here it's already an ABW. We'll just look at one run of the ACW, alternating Kobushi, and that will be like an accepting run for the Kobushi automaton, right? So that's yeah, okay. So okay, so let's try to recall the run DAG that we visited for complementing an NBA. So if you recall that, so there were vertices which are of the form Q cross N. But now you just think of this like it is a run DAG for a single run of the Kobushi automaton. Instead of considering all the possible runs of the NBW, you consider this run DAG corresponding to a single run of of the AC term, alternating Kobushi automaton that we are starting with, right? We are trying to complete that, right? So the vertices are of the form Q cross N, and so Q0 with 0 is the only vertex at level 0, right? We defined Q0 to be the only initial state, right, in our definition of alternating automaton. And we had this infinite sequence, right? G0, G1, G2, correct? So we had this infinite sequence of DAGs, and how we had this infinite sequence is like the G0 is the original that DAG run DAG, which is equal to G. And for every I greater than equal to 0, we had G2I plus 1 is from G2I, we were removing those vertices in the run DAG, which were finite, right? So what was the definition of finite? When did we say that a vertex is finite?
Finitely many vertices are reachable.
Finitely many vertices are reachable. And then G2I plus 2, we removed these vertices where this was alpha free, right? So alpha free is like no alpha vertex is reachable, correct? And then we also saw this. So this is the paper which has this translation, right? The one that we are talking about, right? So we also saw this, that for every I there exists an Li, right? For every I there exists an Li, such that for all L greater than equal to Li, there are at most n minus I vertices of the form QL in G12. So we saw this lemma, right? Right? It had a long proof, but this was the statement of the lemma, and which essentially gave. So the idea was essentially like, okay, so we had these level by level these DAGs, and then we said that for every I, so we considered this run DAG, which is like this G2I, and we said that in G2I there exists some level Li such that beyond that, for all L greater than equal to Li, L greater than equal to Li, there are at most n minus I vertices in all these levels L greater than equal to Li, right? Beyond this, there are at most n minus I vertices. So this is what we showed, right? So we are just restating all these things which we are going to use. And so what does this give us? That in G2n, there are finitely many vertices. Why? Because there exists some Ln, right? There exists some Ln such that for all L greater than equal to Ln, you don't have any vertex anymore, right? So that means G2n has finitely many vertices, and if G2n has finitely many vertices, then G2n plus 1 is empty. Clear? So this is something we all saw. And now, if you recall, so we had defined such a ranking function, right? What was that ranking function? Essentially, in that tree, we saw at which level it is removed, and we put a rank that, like, if it is removed from some Gj, then that particular node, that vertex in the runback had a ranking J, right? So this was the idea. So this is what, right? If QL equal to 2i, if QL is finite in G2i. So essentially it got removed, this particular vertex, it got removed, yeah, from Gj, right? So the maximum rank you can have is essentially 2n, because 2n plus 1 becomes empty. So every vertex will get removed by 2n. When you go to G2n plus 1, no vertex is there. So the last one that gets removed is at most 2n. They may even get removed earlier. I mean, correct. Right. So, and we also define the ranking function in such a way that it would have certain properties, right? That if Q prime L prime is reachable from QL, I mean, we saw these properties like that f of when we defined the ranking function in this way, we also saw that these things would hold true. What? Like if there is a q prime l prime which is reachable from some ql in that runtime G. So if you have ql and then if you are having some q prime l prime which is reachable from ql, then we saw that f of q prime l prime is less than equal to f of ql, right? So we saw this, and we also saw the following, that in every infinite path in G, there exists a vertex ql, right, with f of ql which is odd, and then all the vertices q prime l prime in that path which are reachable from ql, they have the same rank, right? At some point of time, the path, if it's, so if you recall the case of that NBW, when we looked at the runtime, we said that if the runtime is rejecting, if G is a rejecting runtime, then for all paths, you will find that in that runtime, for all paths, you will find a vertex, which is, let's say, QL, such that that will have an odd ranking, and everything that you can reach from there, they will also have the same odd ranking. So it gets stuck in that, trapped in that odd rank, right? And it happens for every path. So this is what we saw. Okay, so this is just a bit of recalling things, and now we'll see how they are going to be used, these properties, in the case of this translation, right? Now, in the case of the Kobushi automaton, this is like, I mean, we are just considering a uh, run, single run. So there is a single like a tree corresponding to that. And instead of rejecting, it now becomes accepting because you don't see the alpha anymore, right? It becomes an accepting run tree. Good. Right. So what we are going to say is that now my state space is of the form Q cross 2n. Okay. So what is this? So this is like, so this set is 0, 1 up to 2n. So this is my state space. Okay. So what is the idea here? Like my initial state will be of this form. So I'm producing, like I'm giving the ranks to those states. Like, so from initially, I'm already giving it to n, and then it will keep reducing. Okay. It will keep reducing. Okay. So that's the idea. Now, the thing is, so let's look at the transition function. I think this is the important part. And the idea is the following, that if this QL, right, in that run DAG, it gets a rank of I, then the automaton here goes to a state, like, so the automaton, after reading that at the lth level, so whatever is the lth letter, so suppose that al, after reading that, I'm going to a state which is of the form qi. So what is the state space again? Like the state space is q cross this set, q cross this set, right? Okay, so this set, and this is the set of all the different ranks that you can have. So you start from that. We know that you cannot have more than 2n ranks, right? So you start with the maximum rank that is possible, and then you are kind of guessing that what my next rank should be. Okay, so if I'm going to, like, suppose the idea is that suppose I'm reading the LH letter, which is AL, and then I'm going to a state which is of the form, say, Q comma I. That means I is the rank of the vertex Q comma L in that runtime. Clear? Was it okay? Or should I say again? So we have this run tree. We have the run tree, right? Like just look at some path, right? And then suppose this is the lth level. I am reading AL. Okay, I may be off by one, like whether you start from 0 or 1. But suppose I am reading this thing, and suppose I reach a state Q. Okay. Now in the run DAG, it will be the vertex will be of the form Q comma L in the run DAG, right? So now I'm saying that I am in the automaton. So in the automaton that I'm constructing, right? This automaton A prime, I will be in a state Q comma I. Okay. I'll be in a state Q comma I. The idea is that f of QL, that the rank that has been guessed for QL, this vertex is I. Okay. So that is the idea. So I'm guessing the rank, and this is how my run is going to look like. Okay. And then I'll show that at some point of time, I get stuck in an odd rank. I get stuck, like if I'm guessing the ranks correctly, then I'll get trapped in an odd rank. Okay. And now, if you see that, like at some point of time, I'll be entirely, like these ranks cannot reduce. I'll be entirely in that set of like these odd rank states. Okay. And my alpha, so I'm going to construct a Büchi automaton. How will my alpha look like? It's the set of states which will be in some state of the form Q comma I, where I is odd. Okay, so that's how my alpha will look like. Okay, because I would like to visit these states infinitely often. Okay, and indeed the thing is that when I get stuck there, right, because of this this particular result, right, this property, so at some point of time I go to that odd rank, right, that odd rank f of ql, and I stay there forever. It's the same odd rank which will be there for all the vertices which are following. Clear? So then it becomes like I'll be staying in some component which I can say qi, where all the states have the same rank I. Okay, all the states have the same rank I. Okay, and I'm going to define a partial function. So I'm going to say that, see, this automaton that I'm constructing, it's indeed a weak automaton. So I need to define this partition. I need to define also a partial order, right? So I will say that all these QIs belong to this QI. All these QIs, they form this capital QI. Okay, so that means that if QI and let's say Q prime I, okay, they both belong to, or Q prime I prime belong to QI if and only if I equal to I prime. Okay, so that's how I'm going to. So I'm just giving you the intuition. We'll see a bit more about how the transitions are defined, right? And so this is what the Büchi automaton will look like. Okay, and it's a weak alternating automaton, right? At some point of time, you are going to see only these odd or states with the odd rank, and you are never going to see any state with any even rank, right? And that's why it's a weak alternating automaton. Okay, right. Okay, so so I start with this q0 comma 2n, and then how does my suppose I am in a state qi, and suppose I read an a, and I say that the transition will be of this form release. So I'll define what this is: release delta of qa comma I. Okay, so the release function is of the form this release of theta I. So what is the release? So maybe I should try to, let's see, okay, let's go over this. I write if equal. So let's look at this. So the release, for as an example, suppose you have Q3 and Q5 comma 2, right? So this is an this is, you can treat this as a rank, and the idea is that I'm going to a possible smaller rank, or at least an equal rank. I'm not going to go anywhere which is larger. Okay. So then what I will have, I'll have something like q3 comma 2 or q3 comma 1 or q3 comma 0. So I can go to any of these states when I'm doing the transition. When I do a transition, then I'll go to either one of these, and I'll also go to one of these. Okay. So I have q3 and q5 comma 2. I'll go to either one of these or to one of these, like that. Okay. So yeah. Now, so the release of theta I, so let's go over this once, we'll come back again and we'll see this. So this is a disjunction of all I prime less than equal to I, qi prime. Okay. So release of theta where q appears in delta of
I think you.
yeah, I think I should have called it q prime and q prime. Delta of q. Okay, so this part, so the release function is clear. So then what is the form of release? Like, so you have, let's say it takes a theta and it takes an index I, right? Index in the set of those ranks that you have. So beta plus q cross 2n, and it gives you beta plus q prime. Okay, beta plus q prime. What is q prime? Q prime is the set of states in the automaton A prime. So this was already of the form some q comma and index, right? So this, it looks like this. So you have the formula, the positive Boolean formula on states of the automaton A prime. Correct? Right? So what I'm doing, I'm trying to get a transition function. I'm trying to define a transition function for the automaton A prime given the transition function of automaton A. Right? So the automaton A did not have the i's. Automaton A prime has the i's. Right? So the delta, like here does not have, it just q comma A, right? It gives you a formula on b plus of q. Delta of q, from this I'm going to define this. That's the idea, right? Now this is something, delta of qa belongs to b plus of q, right? And so I'm saying that now you take this and take an index, okay, and you get something. You have to get something like this. You have to get something which is over the state space of the A prime, right? A formula over the state space of A prime. So this gives you B plus of Q prime. Is it clear? Right? Why the type is like this? Okay. Okay. So for the online participants, is it fine?
Yes. So one question I have. So if the release is of the form Q3 or disjunction Q5, then also it will be something like Q3 2 or
Yeah.
Q3 1 or Q3 0 or Q5 2, like that, right?
Absolutely. Yes.
Okay.
Absolutely. Right. So that part is indeed like, so yeah. So if it is a disjunction here, you will also have a disjunction here. Okay. Okay. So, but you got the intuition behind this. Like we are trying to use this delta prime, and we are trying to guess sort of a rank, which is a not a larger one. You can go to a smaller rank. So, okay. Good. Okay. So was it clear, the idea of how we are defining the delta prime? Yeah. Good. If the current guessed rank is I, then due to the release operation, the run can move to a successor with a smaller or equal rank. So this is what we saw in the release operator, right? You can either stay in the same rank or you can go to something which is smaller. Now there is also one thing, that if Q belongs to alpha and I is odd, right? So then what happens, like, because the rank, it guesses, so if you recall, like it guesses the ranking function, it gives, I mean, it essentially follows from here. The way we defined this, it essentially follows from here, if you recall, that all the alpha vertices, they get an even rank. Alpha vertices get an even rank. It follows from the definition of the F. Alpha vertices get even rank. Now, if you say that I have like a vertex which belongs to alpha and the I corresponding to this is odd, then of course this cannot hold true, right? For such transitions from such states in A prime, you will say that such transitions cannot exist, right? Because this is not a valid thing, right? By the definition of F itself, and hence this is false. Okay, so this is also we have defined. Now, if Q belongs to alpha and the current guessed rank is odd, then by the definition of F, the guessed rank is wrong and the run is rejected. Okay, so this is something we understand. And I say it like this, alpha prime. So you should go and start visiting the vertices infinitely often, which have these odd ranks, right? So we are just, which have these odd ranks, right? So this is my alpha prime. Okay, so this is my alpha prime. Infinitely many guessed ranks along each path should be odd. That's what it gives, right? We are trying to construct a Büchi automaton that we should keep in mind. So infinitely often we should see states which have odd rank. Okay, right. So first, so there are a few things. One thing is that we should try to show now that A is indeed a weak automaton and it is equivalent to, sorry, A prime is indeed a weak automaton and the language accepted by this is indeed equivalent to the language of the original Kobushi automaton. Right? So we are doing the complementation. The first step already did the complementation, but it produced a Kobushi automaton. We are now trying to get an alternating Bushi automaton. Right? So we can just define the classes as this, Q I as Q cross I, and we can define the partial order in this way. If I is less than equal to I prime, right? We can define the partial order, right? Now, by the definition of this alpha prime itself, by the definition of alpha prime itself, right? We see that either Qi is disjoint from alpha prime or it is contained only in alpha prime. Why is it so? Why is it the case? This is how we defined it. Yeah. So go ahead. No, what?
I think like it doesn't it just follow from the definition
Of?
how we got to meeting Japan.
No, sorry. I don't understand what you're saying. So what are we saying? So we are first trying to prove that this is weak, right? In order to prove that this is weak, what are the two properties that we need to show?
In alpha or disjoint
In alpha, disjoint from alpha,
and a partial.
and a partial order, right? So first let's define the partition, define the parts, right? So how do the states look like? The states are of this form, right? The states are of the form Q cross 2n. Okay, right? So this is my entire state space. Now I have to define some Q1, Q2. So these are my partitions, right? Maybe I can have, let's say I was saying that I can have at most up to Q2n, right? So my thing is like, okay, maybe there is also a Q0.
If I is odd, then it is in alpha prime because it's Q cross I
Yes,
when I is odd, and if it's even, then it's different from alpha.
exactly, right? So the way I have defined alpha prime, how I have defined alpha prime is like, so maybe I did not define what does this 2n naught means. So essentially these are like, so the set 1, 3, 5 up to 2n minus 1. This is what this set means. Okay, correct? So all those states which have the second component is odd, right? Because this is how my alpha prime should be defined, right? And now I'm saying my partition is like this. Q0 is my second component is 0. Q1 is second component is 1. So this is clearly in alpha, entire alpha prime by definition. Q2 is not in alpha prime. Q3 is in alpha prime, right? So clearly, so this partition, it satisfies one of the conditions by the way we have defined the alpha prime. Clear? So this part is okay. And now, what about the second part? Like this Qi. So I'm saying that I'm defining this partial order in this form. The Qi is less than equal to Qi prime if and only if I is less than equal to alpha. Why is it true?
Because the transitions are set up in that way, like we are guessing a little.
We are always guessing, right? Because that release operator, if you recall, right? We are guessing it in this way. You go from something which is larger to something which is not bigger than this, maybe smaller or equal, right? So this also gives me the other, that partial order is also, it satisfies the condition which was required for the weak alternating automaton. Clear? So both the conditions are satisfied. So now we are convinced that A prime is indeed a weak automaton. Okay, is it okay? Any question for the online participants? So how the two conditions are satisfied for the weak automaton? Okay. Okay, so now there are two things. We have to show that indeed the language of A prime is contained in the language of A. How do we do that? The language of. So how would you start? Like, let's say you have a word which is there in language of A prime. Okay, now we have to show that indeed this word is also there in the language of A, right? So when you say that it's in the language of A prime, what will you consider? You will consider a run, an accepting run of this word W in A prime. You consider an accepting run. How will the accepting run look like? In A prime, what is the labeling function? Say the labeling function is R prime. How does the labeling function look? How does it look like? It's from T to what? R prime. So this is in general in a run, we have, it's a Q labeled
Q
run.
cross. And
Q cross 2, right? So this is what my R prime is. And if I consider the run in A, how will it look like? T2, the run in A. Sorry?
No, it's a alternating automaton.
yes, no.
Yeah. I mean, in an alternating automaton, just forget everything. So you have an alternating automaton, you have a run. So how is the run labeled from where to where? How does the function look like? The labeling function?
Like it goes to some logical formula.
That is a delta.
Oh,
But if you look at the run tree,
oh, it just goes to some state Q.
correct, right? So this is Q here only.
Okay.
Right? So it's a Q labeled tree. The run tree is a Q labeled tree. Here the Q itself, the Q prime itself is of the form Q cross 2n. This set, right? Correct? So it's, so if you look at just the run, if you look at a run of an alternating automaton, the labeling is always from the nodes, and the nodes are like the set of nodes is essentially the tree. So from the set of nodes to the state space, right? From T to Q. Here just that Q is a Q prime, and in the original one it's that Q is that Q, right? So now all we have to do is like, so if I look at the run corresponding, so I say that, okay, so suppose there is an accepting run, which is like this, right? In A prime, I have to show that there exists a corresponding accepting run in A also, right? So what can I do? What is the most natural thing to do? What is the most natural thing to do?
See the state.
See the state, right? Just project onto this part, right? You have the RAM, which also had the ranking information. Now I look at this, essentially like I just look at that, those states, right? And now if you see that the transitions that you are getting, right? So earlier, in the case of A prime, you will have transitions from such thing to transition to 2 or 1 or 0. Like the run will have one of them, right? Either 2 or 1 or 0. And in the run of A, you will have a transition from, like you will only have this Q3 or Q5, but this also appears, that transition also is part of the delta, right? So it's a valid transition. If you get rid of the ranking of the ranks, it will still give you a valid transition with respect to delta, right? So which means that it's indeed a valid run. The run that you are getting, it's indeed a valid run in A. Clear? Right? So we have to show that the run that we are getting, it's an accepting run. So first we show that it's a run, right? By the definition of the release, the way the release has been defined, right? By the way the release has been defined, and in turn the delta prime has been defined. If I get rid of those extra information of the ranks, I will get a valid run in A. Is it clear? Right? So now I have to show that this is indeed an accepting run. So what is an accepting run in that in the original Kobushi automaton?
Even like, since we are now going to visit the odd states infinitely often, odd states will be like, can be even states alpha states should not be visited infinitely often, and none of the infinite states here will be alpha
Right. So
because of one.
yeah, okay. So we are showing this thing, right? Now, if you show that, let's say I have done this, so now I say that if this is an accepting run, right? So accepting run in LA prime, right? In that, so it means that all paths satisfy the accepting condition, which is alpha prime. Accepting condition, which is alpha prime, right? Which means that you can see only the odd ranks. Now what?
So odd rank would mean in the Kobushi automata, they are not going to be the alpha states, so they can be visited infinitely often.
They are not going to be the alpha states, right? So
Good states, bad states.
yeah. So in the so essentially then what we had is that you only see this alpha prime, and alpha prime, it was equal to this q cross 2n odd here, right? Q cross 2n odd, and that means that only the non okay, so what is that? So if it is only the odd ranking things here, then when we had the states in alpha, right, in the Kobushi condition, they were given the even ranks, right? So that means the states in Q minus alpha, they are visited infinitely often. Right? So this satisfies the Kobushi condition, right? So which means that indeed the run here is an accepting run. Okay, so the run tree T comma R is an accepting run of A. Okay, so first we proved that it's indeed a run, and then we showed that it's indeed an accepting. Okay, good. Any question? Okay. Okay, so what about the other direction? What about, so you just now start with, you just now start with an accepting run in A, the Kobushi automata, right?
And then we just want to give a rank inside that it's solved.
Yeah. Right, you want to give it a ranking, exactly.
So then we could just go by each level.
Exactly. So you just look at, for example, now you consider, so you have, let's say, so now let's say I would consider, suppose I would say, suppose W belongs to L of A, and let T comma R be an accepting run for W in A. Now I have to get an accepting run TR prime, right? So I just look at the, for each level, for each state QL, for each state QL, I know where the rank for that QL, right? I had that, the definition of, from the definition of that G0, G1, we had those run DAGs, sequence of run DAGs. So from that, we also know for each state QL, what is the corresponding f of QL. I mean, I can define my f of QL to be the last that run DAG in which it was there, after which it got eliminated, right? So I can define my f of QL as that. Okay. So now I will say that I'll have correspondingly a TR prime. Okay. Now I have to say that this TR prime is indeed an accepting run for this Büchi automata, for this weak automata. So how do I say that? So first of all, I have to show that this is indeed a run. This is indeed a run. Why? So what is the
Partition will be the levels. Like Q cross I.
Q cross I? But I mean that is already defined, right? So that is already defined in the A prime. So the partition is already defined in the A prime. But what we need to show is that this is indeed an accepting run. Show that this T comma R prime is an accepting run of A prime. Right?
Because at each point, like we are supposed to go to a less than or equal to the rank.
So what about the initial state?
To N.
Yeah. Right. So suppose so the initial state will put, let's say, a rank of the following, that R of epsilon. So this is like this R prime of epsilon is R of epsilon comma 2n. So this is for the initial state, we'll add a rank of 2n. And now every successor will have at most a rank of 2n only, right? So for the initial state, like everything which is so for the initial state, all the successors are indeed satisfying this property that you should get something smaller. Now, let's say
But transition is set up in a way that we are only going to go for a lesser.
exactly, exactly. So our transitions, like, so this was from the run tree itself, like from the original run tree, when we define the level that the ranking function, that itself gave us, like, whenever you are going from one step to another, right? There is a transition in the run tree. Then you are going to a rank which is smaller, right?
Lesser.
Which is less than equal to. So that would satisfy the so what do we need to prove first?
We want to show that the function we are defining here, based on the f, that it is following. Where it's getting from.
So yeah, so one thing we need to show is that indeed so this is an accepting run, right, for W in A prime. We have to show that this is an accepting run in A prime. And A prime is a weak automaton, right? So it should indeed, one thing is that it should get, yeah, so all the, exactly, okay. So it's a weak automaton. So essentially when we are, so we have to show two things. One is that whenever you are making a transition, you are going from something which is a higher set to a lower set, right? Which is going from a higher set to a lower set. And secondly, the other thing we need to show is that it gets stuck in, trapped in the odd rank, right? It gets trapped in the odd rank. So the first property I think is clear enough. Like, so whenever we are doing from the way the f function was defined, right? The way f function was defined, it's like whenever you have a transition in the run tree, you always go from a higher rank to a smaller rank, or not, you don't go to a bigger rank, right? So this part which is required for the weak automaton, so this condition is satisfied. Okay. Now for the other one, what do we do? For the other one, yes, that it will anyway, like every infinite path, it will get
Stuck somewhere.
stuck, yeah, get trapped in an odd rank. It will get trapped, of course, it will get trapped somewhere. But how does it follow that it will get trapped in an odd rank?
Because it's accepting, so we have the odd rank.
Because it's accepting.
So f will be odd.
Why? I don't understand that. So it is
The
accepting.
condition of the thing is like it's going to get stuck.
That is what we need to prove. That is what we need to prove. And in the original one, when we had the A thing, so a run where you have the A automaton, which is the Büchi automaton, there it's like you are going to see only states from Q minus alpha.
And the alpha are the only ones that get the even one. So everything in Q
No,
minus alpha.
that was not the case.
Oh, right. It's the
But alpha can't be in the odd thing.
Alpha can't be in the odd.
That was defined in the transition earlier.
Yeah.
Yeah, alpha cannot get the odd ranks. But Q minus alpha can get even ranks also. Right? So what was the thing? Like, so you recall that, let's say, let's try to go over this a bit slowly. So you recall that there is a run, right? So this is a run in the Kobushi automaton. In the Kobushi automaton A. Automaton A. Okay. Now this doesn't see, so this gets stuck in Q minus alpha. It's an accepting run, correct?
Yeah.
So this gets stuck in Q minus alpha, correct? Now it may be possible, so alpha vertices will always get even ranks. Alpha vertices never get odd rank. But the vertices in Q minus alpha, they may get even ranks also.
But we have that theorem, right? That it
Ah.
will get stuck at
Ah.
odd.
So
It
now
is
we use that result, which said somewhere that in every infinite path in G, there exists a vertex QL, which we saw earlier, with f of QL being odd, such that all the vertices Q prime L prime in the path which are reachable from QL, they have f of Q prime L prime equal to f of. So indeed, so your all these paths, they indeed get stuck in an odd rank, right? So that's what this result says. So it requires this result. And this will say that indeed, like the rank that you are going to get, that if you are going to get eventually, this is odd. Hence, this is accepting by the definition of alpha prime. Okay, right? Yeah. So it's all about like using that result, and the other things are a bit of these definitions. So only thing is that we are using that result here once, that result. The other things are just the definitions. I mean, it's just that we have to keep the definitions in mind, and then it's all the good things, right? So I think we more or less we have covered the result. It's just that you should. Oh, I didn't look at the time, but okay. So now, yeah, you should just go back and look at this paper. It's a very beautiful paper. You must, I would say that you must always, you should all read these parts, right? So this is referred to in the chapter, but the construction is not there in the chapter. So you should try to see and okay. So I okay. So with one so we now have this, like given an ABW, we have an ABW with order n square states. With one last comment, I would finish. Let's say okay, we did not do the alternation removal yet. So which maybe we'll do during the next lecture. So this will be very interesting. Like you do the alternation removal, and there will be several things we'll see how they are related. For example, the relations between this was possibly this slide, like how these things are all related, like NBW, then DBW, ABW, ACW, NCW, DCW, right? So all how they are all going to be related, right? So this is something we'll see. So this is a very well-known and important. It's not too difficult. It's a relatively simpler construction. It's called the Miyano-Hayashi construction, or people also call it a breakpoint construction. Okay, so this we'll see in the next class, which will be on Monday. So we are not having a class on Friday because I won't be around. And that's so we'll have it next Monday. And we'll also look at some of the decision procedures for ABW, like whatever we saw for NBW, like non-emptiness, non-universality, containment, all these problems for ABW as well. And once we do this Miyano-Hayashi construction, we'll see some of these things, that NCW and DCW are equally explicit. Okay, and similarly, we'll try to understand these things, how expressive are NBW, DBW, ABW. I mean, we already know this part, right? ABW, we say that we can remove the alternation, so this becomes same as this, and DBW is strictly less expressive. And so we'll also see for the Gomushi automata. Okay, so let me stop here. Stop the recording.